Hi everyone, in this part of the video I'm going to go through the sort of inequalities part of this section. So remember, when we're solving inequalities, the way that we want to do this is solve it like it's a standard function. So I'm going to get everything over to one side and then solve it. Since this is a cubic function, the best technique to do is to use group factoring. And so if you remember, the goal of group factoring is to factor out a GCF on both the left and the right so that the common factor stays the same in the parentheses. So in this case, I have x plus 2 inside. So this factors to be x squared minus 1 times x plus 2. That's got to be greater than or equal to 0. Now this can keep factoring, minus 1 plus 1, x plus 2, greater than or equal to 0. And so I've got three potential important points here: positive 1, negative 1, and negative 2. Now with that, what we want to do now is we want to plot them on a number line. Negative 2 goes first, negative 1, and positive 1. And so we're going to just test points. Now I'm going to use a different color here just because that's going to help me distinguish them a little bit better, as well as my normal sort of setup here. That's a negative 1.5, by the way. And so I want to plug these in to determine whether it's just a positive or negative. And if you remember, I told you before, this is the most ideal way to plug it in, because I just need to kind of keep track of what type of number I'm multiplying. So for example, if I plug in 2 first, if I plug 2 into here, I get 2 minus 1, which is a positive. If I plug 2 in here, I get 3, which is another positive. If I plug 2 here, it's another positive. So I'm multiplying 3 positives together. So that means that value will be positive. If I plug in 0, I get negative, positive, positive. If I plug in negative 1.5 into this function I highlighted here, I get the first term would be negative, the second term would be negative, third would be positive, meaning that that term is overall positive. And then when I plug in negative 3, I get negative. So when the function is greater than 0 would be all the intervals in which it's positive. So negative 2 to negative 1, and then union from 1 to infinity. Now when I have something with an inequality of a rational function, I need to subtract 2 on both sides. And I can't really do my subtraction like normal, so I'm going to have to make this a common denominator. And again, I'm going to do it in red. So I want this to have x plus 3, which means I had to put in x plus 3 up top. And so I'm going to distribute my distribute my 2. So I get 2x plus 6 over x plus 3. And so if I actually do the subtraction, x minus 2x gets me negative x. Negative 2 minus 6 gets me negative 8 over x plus 3. In this graph, or inequality I should say, I know that my vertical asymptote along with my x-intercept are going to be problems. So at negative 3, I have a vertical asymptote. And at negative 8, so I'm going to have to revise my little graph here. So negative 8 is my x-intercept. Negative 3 is my vertical asymptote. And so now I'm going to test points in here. 0, negative 5, negative 10. And again, when I plug them in, I'm only concerned about whether it's positive or negative in this function. So if I plug in negative 10, my numerator will be positive, my denominator will be negative. If I plug in negative 5, I'll end up with negative over negative, which is overall positive. And finally at 0, I end up with a negative. So I want all the intervals in which the graph is negative. So that's negative infinity, negative 8, negative 3 to infinity. And that's it. Now with these complex number ones, you should just remember our general rule. Combined the same real or complex parts. So here it would just be 2 from the negative 7 and 9 plus 10i from the I pieces. Number 10, since it's squared, I'm going to write it twice. I'm not going to individually square them. That's not a thing we can do. And I have to distribute. So 4 plus 6i plus 6i plus 9i squared. And important to remember, if it's I squared, it's really a sign change. So my final answer is negative 5 plus 12i. Here, since it's dividing, we have to multiply by its conjugate, 4 minus 3i in top and bottom. So with some distributing up top, I end up with 12 minus 9i minus 16i plus 12i squared. In the denominator, I get 16 minus 12i plus 12i minus 9i squared. Again, the whole idea about conjugates is that it's going to cancel the imaginary part in the denominator. So now it lets us actually work through all of this with no complex numbers anymore, in the denominator at least. So this is really plus 9. So 16 plus 9 is 25. And then going forward in the numerator, this 12i squared is really the same as negative 12. So 12 minus 12 is 0, so I actually just end up with negative 25i, which simplifies all the way down to just negative I overall. In my next piece, this is going to just take a little bit of multiplying out. Not too rough though, it's just a little exercise in patience. What I'd actually recommend is leaving it in 2 parentheses and now doing this multiplication and then doing the subtraction at the end. I wouldn't distribute with the negative. We're more prone to end up distributing twice or making an extra calculation error. It's easier for us to just do the subtraction at the end. So here 2 minus 3 gets me negative 1. Here this is 5i. In this, again, these were conjugates, so the i's go away, but the I squared becomes a plus 1. Oops, that should be positive 10. And so here, see, it's a little bit nicer to say negative 1 minus 10, negative 11 minus 5i. Okay, and that's all of those. Now, for my next piece here, write the 4th degree root function that has these roots. So if you remember, the difference between a root and a factor is changing the sign inside the parenthesis. Now, you should be looking at this saying it's a 4th degree, and you only have 3. Well, if you recall, we've always get plus and minus I terms in roots. The reason for that is because, think about doing the quadratic formula, we always get the positive and the negative. And the only way for us to produce those roots is by using square roots, by completing the square or the quadratic formula. So if I know I is a root, then negative I must also be a root. So now we can distribute all this. Again, another recommendation I have, do this in 2 pieces and then distribute at the end here, because when you do that, it actually is easier. It ends up being a lot easier than most people think it will be. So this is x to the 4th plus x squared plus x cubed plus x minus 6x squared minus 6. And I only really have one piece to combine here, so x to the 4th plus x cubed minus 5x squared plus x minus 6. Okay, and so for our last set of problems here, finding the roots. Now you can use a calculator for some of these, so we'll go through how we could use a calculator to solve. But we're going to have to use the rational root theorem. So remember your p over your q. My p is 1, my q is 3, meaning all my possible roots are 1, 3, and 1/3. Now, looking at this function, I don't think there's going to be any possible roots here. So I may be tempted just to go right into quadratic formula, because the quadratic formula will actually tell me. Now, maybe I'm wrong. I don't have my answer key in front of me, which is why I'm doing it this way. But just looking at these numbers, 1, 3, and 1/3, I'm not sure I exactly trust. So when I do quadratic formula, negative b plus or minus squared b squared minus 4ac all over 2a, we end up, actually it should be a plus 12. We end up with 12 plus or minus the square root of 156 over 6. So this was not rational, because if it was, the square root, the discriminant part, would be a perfect square. So since this is not a perfect square, it didn't quite work out the way we wanted to. But we can reduce that by square root of 4. So that would be the square root of 4 and 39 over 6. So 12 plus or minus 2 root 39 over 6. All the whole numbers are divisible by 2, so we're going to make this 6 plus or minus the square root of 39 over 3. And that's the most simplest version I can state for these roots. Okay, and then my last one here. So this is a quartic, so we don't really have a way to do this other than using the rational root theorem. Now, good news is Q is 1, so that just means all my possible roots are the factors of 24, which are these listed right here. So I'm going to list them out real quick. 12, 24. Let me double check, make sure I got all those. Yes, that is all of them. I just had to double check. So, just from doing this problem earlier, I'm not going to start with 1 because I actually know that the first root is 2. So remember, we're going to do synthetic division. It's 1 and then 0, negative 6, negative 8, and 24. Remember that 0 comes from the fact that I don't have an x cubed term, but I need a placeholder for it in the division process. So bring down my first number, 2, add. Okay, and we get 0, so we're excited about that. Now, this does give me an answer, but we have to remember that I bring it down by 1 degree, meaning it's a cubic. So that's still not really easy to factor. So what that means is I'm just going to continue the process, and believe it or not, I know my next root is also going to be 2. So when I do this, that's 8, that gets me 6, that gets me 12. So now I am left with both of the roots being 2, which means my factor will be x minus 2 squared. And what I have left is x squared plus 4x plus 6. And so if I try to factor the quadratic here, it's not going to work. I could even try looking at my roots, and we're kind of seeing like, yep, we got to go back to using the quadratic formula. Or maybe you want to do completing the square this time. But the numbers are pretty small, so I think it'll be quicker for me to do the quadratic formula. So we get negative b plus or minus square root of b squared minus 4 times ac, which gets me minus 24 over 2. Now when I look at this, that looks like a complex number in my square root. So that's going to be I square root 8 over 2. And if I break down the 8, I get 2I root 2 over 2. Whew, almost done. And since all my whole numbers are divisible by 2, I'm going to do that. And so my 2 roots are 2 with a multiplicity of 2. I shouldn't say 2 roots, sorry. There's 3 roots. It's just that they are paired. And 2 plus I root 2 with a multiplicity of 1, and negative 2 minus I root 2 with a multiplicity of 1. Okay. All right, well, that was a lot for this one page alone. Oh my goodness, I missed a problem. Holy cow. So again, let's do this one real quick. So remember, we can't actually multiply with negatives inside square roots. So I'm going to change that first. And you know what? I just simplified square root of 8. But believe it or not, I'm not going to do that right now. And you'll see why. So when I distribute, I get negative 4 minus 2I root 8 minus 2I root 8. And this is why I didn't. Because when I do this multiplication right here at the end, it's much easier because square root of 8 times square root of 8 is just 8 itself. So now again, this is going to be negative 8. So negative 4 minus 8 is negative 12. This piece right here is minus 4i root 8. And when I break down the square root of 8, I just did that. It's 2. So we get negative 4 times 2 is 8i root 2. Oof. All right, so that was a lot for this page. So I'm going to stop it here. And then in the next part, we'll hopefully be able to finish. But yeah, thanks for following along there. And let me know if you have questions.